We can start the show. So, welcome back. Thanks for being here. 2 more weeks of classes and then finals week. So we're all in the countdown phase of the program. It's nice to know that the end is in sight and we can all collectively exhale in a few weeks. So with respect to homework 5, that's due Monday. You all have turned in plans and then revised plans, so hopefully we're on the same page with respect to what you're doing. But if you're not sure what you are doing or how to be doing it, please let us know. We're happy to help you. Vladimir suggested maybe we talk about interaction terms as a brief review. For those of you who are attempting to fit moderation models, I know there's quite a few of you who are trying to do that. This is lecture 1 that I have back open. And yeah, that was like 3 months ago, so if it doesn't look familiar, then that's why, because it's been a minute. So interaction terms, the big idea is that in order to talk about what they do, we don't talk about what they do to y as a predicted outcome. We talk about what they do to this main effect slopes for the variables that are part of the interaction. So for instance here, if I have a model that looks like this, and by the way, what I'm about to say is absolutely not different if you are predicting logit y or probit y or log y or proportion y or whatever, right? All of the generalized part is on the left-hand side of the equation. The linear predictor part, the rules as to how you think about intercepts and slopes are exactly the same. So in this example equation here, beta 0 is my intercept that gives me my predicted outcome in whatever link metric, logits, probits, etc., when all this stuff is 0. If I had this effect of predictor W, this is unconditional. W is not part of any interaction terms within this model. So that means that I would talk about beta 1 as what happens. Oh, I forgot to share the screen. Thank you. Sorry about that. I'm on lecture 1. Impromptu review. Beta 1 is the effect of W on Y for everybody. So it's after controlling for the effects of X and Z. It is the unique effect of W, but we don't have to say conditional on X of 0 or conditional on Z of 0 because W doesn't interact with these other things. So in terms of like vocabulary, I would call this a unique effect and it's a marginal effect, meaning that it is not conditional on any particular level of a predictor. The same is not true for these two, though, because of the interaction. So beta 2 is only the slope of x all by itself when z is 0, because that would be the point at which that interaction term drops out. Likewise, beta 3 is only the effect of z all by itself when x is 0, because that's when the interaction term would drop out the other way. So to talk about moderation, beta 4 is going to take each of its main effect slopes. So beta 4 applies directly to beta 2 and beta 3 here, and it makes them more positive, less positive, more negative, or less negative as a function of the other variable. So beta 2 can get stronger if z increases. If this were 2 positives, for instance, beta 2 could get weaker if the signs were in the opposite direction. So which way you talk about it is entirely based on your research question. If you are thinking about a variable as a moderator, like I want to know if this relationship differs in this group versus that group, then logically what you would want to report is what is the relationship in this group, what is the relationship in that group, and are those relationships different via the interaction term? You wouldn't necessarily want to go the other way. The rules for how to figure out how to get a simple slope, we always start with what's in the equation, factor out any terms that have the predictor the slope is 4, and then what's left are your ingredients to form a simple slope. So for instance, if I have, let me get down here, zoom in a little bit. If I want to know how to figure out the slope of x for any level of a z moderator, I start with the main effect, I start with the main effect of x, here it is, and then I add in the interaction, factor out the x since that's the variable the slope is for, and then the part in brackets, it's what's left. So you would only need to compute this for non-reference values. If you have a slope for a reference value of your predictor, then it's already going to be in your model somewhere. Okay, does that help maybe? Yes. Or anyone want to talk about their model more specifically? On the basis of this, free help, free consulting right here. No? Okay, well, let us know. We're all happy to try and help. If you are reporting interaction terms, then I would expect at least some follow-ups in terms of simple slopes, specifically any slope that is part of a research question. Your analyses ideally should be phrased as answers to questions. That's the practice that I'm hoping for. So not just plug and chug, but also trying to describe it verbally is an important skill. All right then. Anything else you want to talk about with respect to homework 5 or other stuff? No one wants to talk, period. Like, we're here. What more do you want from us? Fair enough. I'm here. I'll do the talking. We are contractually obligated to keep meeting. How about we change directions then and talk about some cool shit? Path models. Yay, path models. It's like the grand finale. Another point of overlap, but this is not the same thing as what we're doing in the SEM class because I'm not doing latent variables. So this unit is what your last homework is going to be about. Homework 6, which is due at the end of finals week, I will let you know when that is available, will be a path analysis. You will be able to use either Lavon and R to do it or M+. All of you should have access to M+ from inside the U Iowa virtual desktop. I arranged for that several weeks ago. Please check to make sure that you have access to M+ if you want to be able to use that. I teach using M+ in the structural equation models class, so getting to be able to use it now would be good. I also use it in some of the longitudinal models class as well. So it's a very versatile software package. Costs a lot of money, which is why it's important to have free access through the university resources that we pay for instead of you. But path analysis are path models. Broadly construed are multivariate models for predicting more than one outcome at the same time. So it's a bunch of simultaneous regression models. You can incorporate link functions and alternative distributions, so it is general and generalized. The difference is that software limitations make it more difficult sometimes to do the generalized versions, but it would be more flexible than trying to trick a univariate software package into doing it like we saw last time. So to be able to do this, though, even though like conceptually it's fairly straightforward, there's a lot of vocabulary and additional words and things that we have to learn. So that's the starting point here, is just trying to get used to how people present these things and how they talk about them and the words that they choose. So away we go. Lecture 6, the last unit, I should say. So in terms of general versus generalized, if you pick up a book on structural equation modeling or a book that has path analysis as part of that, in almost every case they're going to focus entirely on the general linear model version, where everything is assumed to have multivariate normal residuals. So a lot of what you will see is customized to that, doesn't necessarily directly extend in some cases to the generalized case. I want to try to show you examples of both, though, because I think it's useful to be able to do that. So you can do path models in a whole bunch of different software packages. Even back in SAS has ProcCalus since I think it was from the 80s or 90s even. Stata has a SEM package as well as a GSEM. M+ is the one that I use that's the most flexible. Lavon is a package in R that's very commonly used and is pretty good. Lizral was the very first package ever made for these things back in the late 70s. I learned how to do path analysis and structural equation models on software called EQS as well as AMOS, which is within SPSS. So there's a lot of choices for fitting these things. One thing that they all have in common is that from this point forward, denominator degrees of freedom are not a thing. All of your WALD tests are going to be given as Z's for single terms or chi-squares for groups of terms. So that part is we've seen in generalized models as well. And I have the second half of example 5 that we started working on before with the moms, dads, and adult children doing path analyses to try to show you the mapping of how it would look like as a linear model versus this, as well as a full mediation analysis in example 6a. Generalized options are harder to find and always require more complexity and estimation. So the G in Stata GSEM, I think, stands for generalized. It also has multi-level, so I don't know why they didn't throw an M in there too, just to cover their bases, but whatever. Lavon has link functions for binary or ordinal only. M+ also has counts and zero inflated counts. GSIM, I want to say, is the only one that I've seen binomial anything in. That one is harder to find. I do have an example with 2 binary outcomes to do mediation where those are the end of the chain. And Vladimir has one. I haven't talked to you yet, but if you want to do your nominal example from last time, again.
If we have time.
If we have time. Yeah, we'll see. We'll see. But
Yes.
there is a nominal example we can give you as another example of this.
Yeah.
So the catch with this in terms of estimation is that the direct way of introducing residual relationships, so like allowing the residuals from the same unit to be correlated, doesn't work if you don't have a residual variance as part of your model. So any of the generalized versions, we have to introduce relationships through latent factors called random intercepts instead. So that's one additional piece that makes it more complicated, and I'll show you what that looks like, because I learned how to do that too late. So I want to save you from the same fate. Yeah.
I mean, we can use state up not n plus to do the path analysis.
So in your homework, I'm going to say no, because I can't guarantee that the results will be the same to 2 or 3 decimal places. In your life, yes. And I can help you in either case.
Thank you.
Yes. Nikki, have you played with the SIM and GSIM much in Stata? Any thoughts?
Actually, when I took this class, I started in Stata, and they were actually pretty close in terms of numbers. There was one thing that I had to convert to. I didn't follow the rules.
You didn't follow the rules. Well, actually, you being a troublemaker could come in handy, because when I put up homework 6 for testing, you could try it in Stata and tell me if you get all the same answers or not.
Great.
So we
I will do that.
to be
That'd be
continued.
helpful. Thank
Yeah.
you.
Yeah, to be continued. We'll say that. Yeah, as a general principle, the more complex the model, the less it's going to agree exactly across packages. And that is especially going to be the case for anything generalized, as well as things that have latent variables and random effects for like multi-level variance. So, to be continued. Yeah. All right. So, another thing that differs across packages is what you can do with respect to estimation and how that interfaces with missing data. And this is where you will see older material make claims that are no longer true, and it is a function of what was available at the time in software. So this is things change fairly rapidly with these models, and so I'm trying to give you what I believe to be the most up-to-date, but these even may have changed since the last time I looked at this. So in estimation, we're using maximum likelihood still. By the way, for those of you who've had the multi-level coursework in which we used Dremel for everything, that is not a thing in path models, so that's not even a choice. For multivariate normal outcomes, there's 2 different options as to what happens to incomplete cases based on your estimator. So the term full information estimator, otherwise known as FIML, so F-I-M-L is pronounced FIML. This is a term that means we are using all of the original data to estimate the model. When that happens, you can include cases that have incomplete information to at least some extent. If you are using instead what is known as limited information maximum likelihood, that term means that you are estimating the model based on a summary of the data instead of the data themselves. So for instance, if you read a research article that reports a path analysis, and they provide you with the correlations among all the variables in the path model, along with the variances and the means of those variables, you can recreate their analyses. You can provide that correlation matrix and mean vector and variances as input to a software program, and you can do whatever analyses you want. But they would be limited information, and that means that you would not be allowed to have missing cases. Basically, the summary has to be internally consistent with the cases that it was created using. Nowadays, people would never do it this way unless they were stuck with archival data. Full information is the default in all the packages. Another distinction that you will see is whether or not your estimator is robust to deviations of multivariate non-normality. So this is a workaround for when you're predicting things whose residuals are probably not going to be normal and homoscedastic, and you want to try to adjust or hedge your bets in terms of the inferences that you make by doing what is known as a robust correction. So on your reading list, Ender's Chapter 5, it's actually a missing data textbook, but he talks a lot about how maximum likelihood works in the case of missing data as well as robust. It's the best explanation of this that I've seen. So I put it in all my classes so that people can benefit it because he does a much better job at explaining it than I can. But what I can tell you from my brief recollection of this is that there is a condition in which if your data are perfectly multivariate normal, some ratio holds of the first derivatives of the likelihood function to the second derivatives. And to the extent that your data aren't normal, that ratio doesn't hold. So it computes what is known as a scaling factor, which is based on that ratio and uses it to try to correct the standard errors of your parameters as well as the fit statistics of your model. So you will see this pop up into the discussion as well in M+ as well as in Stata. They have robust options for that. But it simplifies to regular ML if you have multivariate normal data, so you can think of it as a default. So you'll see a couple examples that have this version of the estimator, in which case you would have to do likelihood ratio tests a slightly different way. The formula for those is a little bit more complicated, as shown on slide 4. Here's a link to where it's explained in M+. And I also have spreadsheets from my SEM class that use this version of the likelihood ratio test linked here. So this version takes into account the scale factors in computing the difference parameters here. So still the straight difference, then we correct it with the scaling factor correction here. So you will see these things. The word robust means it's trying to help non-normality. That's the key thing here. All right, picture time. So path models are nice because you can clearly show to a reader what all is going on at the same time in a way that an equation would become overwhelming very quickly. So path models are conceptual models that are very useful for communicating what you're trying to do. And it's one of the few instances in which the world has agreed on diagramming conventions. So in a path model, anything that is in a box is a real variable. It is an observed column in your data set. Anything that is in a circle is imaginary. So it's either a latent variable or it is a residual of a variable that has to be found after estimating the model to predict it. Arrows come in one-headed varieties and two-headed varieties. A one-headed arrow is a slope, and it is a slope that goes from the predictor to the outcome. So the end of the arrow is the y variable that's being predicted, such as down here in this picture. If you see a two-headed arrow, such as the one that is attached to y2 right here, that is used to indicate a covariance. So between y1 and y2, this blue arrow with two heads is saying y1 and y2 just get to be related. The arrow pointing into itself, a covariance with itself, is known as a variance. That's another way that people describe the idea that this y2 has an estimated variance to it. Explicitly showing the e as a separate latent variable is another way. So either of these you will see in practice in terms of the idea that y1 has a variance left over. Here's e explicitly, y2 has a variance left over with the two-headed arrow going into it. So this picture right here describes a system of equations predicting y1 and y2 simultaneously, in which the x1 to y1 path is labeled here b with y1 in the superscript and x1 in the subscript. That's a convention that I'm using here. That's not always the case, just to try to keep track of what's being predicted from what. So this model says that y1 is being predicted by x1 and x2. y2 is also being predicted by x1 and x2, and y1 and y2 get to be related to each other. So in terms of what it would look like as a linear model representation, that's over here. In terms of what the error structure would be for the two outcomes that are related, y1 would get its own residual variance, y2 would get its own residual variance, and then there would be a covariance between the two. So this is completely up to you in practice when you're estimating these things. Do you think something is a predictor? Do you think something is an outcome? Or do you think that two things just should be related and not in a directional fashion? Just related is a covariance. Outcome of one or the other, these arrows are called path coefficients. They are fixed slopes. So you will hear me switch my language when I start looking at these pictures from slope to path. Those are synonyms. Two-headed arrows are not called paths. They're called covariances because that's what they mean. Okay, how are we doing so far? Have you seen pictures like this in research papers? Things? particularly in like grant applications, showing in like a conceptual model of to like what the pieces of your analysis are going to be. I would not have all the parameters labeled on those, but it can be helpful as a communication tool. In this model right here, this is two separate univariate regressions happening simultaneously. There really is no reason why I should have to fit this particular set of equations as a path model. Why I would do that is if I were interested in testing differences in effect size. So for instance, if I wanted to know if x1 was a better predictor of y1 than it was with y2, then I could ask that question, whether the path from x1 to y1 is the same as the path from x1 to y2. I can set a constraint, as it is called, tell the model, hey, make these two numbers the same and tell me how much worse it fits. And if it fits worse, then you shouldn't make it the same. You can also directly get a difference as a wald test like we've been doing all semester. Another reason that you would want to go to the trouble to do a path model to predict two things at the same time is if one of them is going to become a predictor and an outcome in the same analysis. I'll show you a picture of what that looks like in just a bit. So this type of framework, if it's estimated in dyadic data, has a special name. They're called actor-partner interdependence models. Did I get that right? APIM, actor-partner models. And I am physically incapable of not making this gesture when I talk about these, because this is what it looked like. So if these were data from, say, a mom and a parent, or a mom and a kid, let's go with that, then we would have something like, does mom's predictor predict mom's outcome? Does mom's predictor predict the kid's outcome? So mine to someone else's is the partner part. Mine to mine is the actor part. So these are special names in that context, but it's nothing more than a multivariate regression. Question from the Zoomers, do I have an actual example of how to apply this to real life research? Yeah. So actor-partner models would be one example. Anytime that, like I said, you're interested in differences in effect size, does this sound like it would be useful to any of you? Does this sound like something that would be up your alley? Any specific examples coming to mind? No. All right, let me skip to answer your question with a specific example. Let me skip way ahead, I think. Do I have a picture in this one? No, it's the other slide deck. I don't have a picture of this one, but I can. If you'll permit me to cross-pollinate the classes yet one more time. I just put this in the other slide deck for SEM. Let me show you an example of a path model that has that actor-partner flavor. This, okay. So the reason I put this slide in there was to show you how to abbreviate path model diagrams so they don't go insane. That was the purpose of the slide, but it actually answers this question too, so let's go with it. So this is from a publication that I helped with, a former graduate student at one of my previous universities, and they had an experiment in which they were trying to deplete people's self-control and then see what happened. And this is in dyadic data in which they had two people from the same partnership. So it's divided by gender, but the same would hold in various other kinds of dyads. So we have, for instance, woman's pre-conflict negative emotion reactivity, that times self-control depletion condition. So that was the manipulation as to whether or not they had to be depleted or not, another interaction term. And all four of these things are collapsed into one arrow that has the letter A on it, for this is an actor effect, because all four of these variables are going to predict this outcome right here, which is intimate partner aggression. So kind of a similar story as before. How many mean things you're going to say to somebody? Likewise, on the men's side, we have the same information collected from them that feeds into an actor path to their outcome. And then the cross ones here that are labeled with the P's, those are the partner effects. So this has 1, 2, 3, 4, 5 paths on it, but those 5 paths conceptually represent way more arrows than that. Self-control depletion has a main effect because couples were randomly assigned to one condition or the other. And then last but not least, the little e's on the end of the boxes have a two-headed arrow, meaning that those outcomes get to be correlated within dyads. So path models are useful for regression of lots of things at the same time. They're especially useful if you want to contrast the size of relationships from one set of variables predicting an outcome versus another set of variables predicting an outcome, and such as, are the actor effects stronger in men than women? Are the partner effects stronger in men than women, and those kinds of things. So there's my example. How was that? Hit me.
So is this the same as like mediation, moderation?
This one is not. Technically, these boxes right here that have the interaction terms, that would be moderation. And this is the proper way to show a moderation is as a separate box because you're literally making a multiplicative combination and sticking that in. This would not be mediation though because that would require two chains. So mediation is like x to m and then m to y, whereas like all of these are clearly x's and all of these are clearly y's. Mediation is coming many, many slides from now. Here. Slide 40 will answer your question. Mediation looks like this. So you may have multiple mediators, multiple outcomes, multiple predictors in the model, but the idea is that like x causes m, m in turn causes y, so the reason that x and y were related is mostly because of m. That would be mediation, and in order for that to make sense, it has to be something where like m could be logically caused by something. In contrast, a moderation model is often depicted this way. Like this is a conceptual moderation picture, but that's not accurate. To actually show what moderation would look like, you would need an interaction box. So x and m are both predicting y. They interact to additionally predict y. So that means the effect of m depends on x, the effect of x depends on m. But in terms of the layers, there's an x layer and there's a y layer. There's no middle layer like there is here. So most of the time you can do moderation, but mediation is not always logically possible. So I once had to help with the grant analysis plan, for instance, in which they were interested in testing mediators of age. Yeah, that noise, that's what I said. I was like, how do I say this politely? So let me get this straight. I have my predictor. It's going to cause me to get older. And then the fact that I'm old is going to cause this outcome. Well, there are some things that cause you to get older. I will tell you, graduate school, parenting, marathon training, but mostly it's just the calendar that causes you to get older. So no, what they meant was age is a moderator. They thought relationships would play out differently in older people than in younger people. That is the bottom picture right here. So mediation and moderation are not synonyms. Moderation means interaction terms. Mediation is this idea, but to me, it's just regression with a better marketing campaign. Because what you're really asking is, what is the effect of x on y after controlling for m? And that's just, any regression model will tell you that. It's just this additional piece right here allows you to look at everything simultaneously. And this type of model is ideal for path analysis because m is both an outcome of x and m is also a predictor of y. So m has two different roles to play. Okay, does that help? Yeah. Word soup. It's not just word salad. It's like soup and salad, like a combo meal and all of these things. Yeah. It's like the Olive Garden of modeling, I think.
Oh, have them separately?
Yeah, soup and salad, like.
I thought
Yeah.
you meant soup and salad.
No, that would not go well.
Yeah.
Yeah, no, I would not recommend putting your salad in the soup. Although, so I worked in college, I waited tables at a restaurant called Grisanti's, which was essentially an Olive Garden that had bread loaves instead of sticks. And we served hot marinara sauce as a dip for the bread. And whenever we brought out the salad and bread as the first course, invariably at least once a night, someone would look at the salad dressing, think it were French, and dump it on their salad, think it was salad dressing, and dump hot marinara sauce all over their salad. And then I'd come back and I'd be like, Would you like a new salad? Yes. I just ruined my salad. The fact that the salad dressing was steaming, I think, should have been a clue. But it was not always very well lit, so we'll give them a grain of salt. But no, marinara sauce, not an ideal salad dressing. Anyhow. All right, answering questions. I feel like I'm on a quiz show today. Like, who's next? Bring it. I'll see what slide deck I can roll through off the top of my head. Well, there's only 48 slides on this one. I mean, good thing we only have 3 weeks of class left, right? Okay, where are we? This one, we did that, we did that, we did that. Yes, we're up to here. Okay. Just as in regression, this is slide 7, back in our regularly scheduled lecture 6 for this class. In regression, you end up with an unstandardized solution and potentially a standardized solution. I have not made much use of the standardized solution this semester because there's really not a direct analog once you lose residual variances as a thing. Like standardized solutions and generalized models are not really that useful. But in path analysis, you will often see people report a standardized solution. So the original regression model, as it would be fit here to predict Y1, for instance, is scale specific. So beta 0 is the expected outcome when these predictors are 0. These describe the change in Y for a 1-unit change in X, and then E would have a variance that plugs in whatever is left over. Standardize, Z scores all of the variables in the model, predictors and outcomes first, and then fits the model to those standardized versions. So every variable would have a mean of 0 and a standard deviation of 1, which means that the model parameters are then trying to reproduce the variables' correlations as opposed to just their variances and covariances. One of the reasons why I'm not a huge fan of standardized slopes is because what's being standardized is not the right variance. If you have 2 variables, X and Y, then the standardized slope that you would get out of a regression model of one predicting the other would be the Pearson correlation between them, right? That's unambiguous, so it's just representing the bivariate information. But then to the extent that you have multiple predictors and they're related, that is no longer true. The slope that you get for each predictor relating to an outcome is the unique effect, right? It's the part of the predictor's unique variance that predicts Y. But the standardized solution doesn't standardize the unique variance in X that's relevant, it standardizes the whole thing. So it's not really a standardized slope in the way that we would want to think about it. As it turns out, what you actually would want to have is a semi-partial correlation, but there are no path model softwares that put that out for you. So standardized solutions, for better or worse, are very, very common. They are the easiest way to try to contrast effect sizes for predictors on different metrics, and so they're useful in that despite this limitation. So you will see this version of the solution most commonly reported in practice because people tend to have an easier time interpreting these without having to know what the scale is from. All right, new and confusing terminology about what endogenous and exogenous mean. And this is something that I think it depends on who you read and what software you're using based on what it means. I'm going to try to simplify it for you, but let me explain what the problem is. In this literature, variables that are predictors only are known as exogenous, and variables that are outcomes are known as endogenous. Here are the mnemonics that I use to keep track of this. So I think of predictors as x's in my notation. So exogenous means it's an x variable to me. Likewise, endogenous means the arrows are going in, so it's endogenous. So in this example that we just saw, I have 2 exogenous variables, x1 and x2, because they are predictors. I have 2 endogenous outcomes, y1 and y2. They are not predictors, they are only outcomes, and they are related to each other. And in M+, this is all you would need to write to fit this model. M+ has 3 keywords to it. On means a directed path, with means 2-headed arrow, and by is a factor loading. That was the previous class. We don't need that one in this one. So what I would be saying in this code is I would like x1 and x2 to predict y1 and y2. So listing both outcomes on the left and both predictors on the right renders all 4 of the possible slope combinations that are in this picture. And on, you can think of as an equal sign in your head to make sure you get the sides right. Like in an equation, it's always y equals x, and it's always written from left to right in that order. At least everything I've seen looks like that. So in my head, I always replace the on with an equals to make sure that I've got the outcomes on the left and the predictors on the right. With then is the covariance between the residuals of y1 and y2. If I change the model to look like the bottom picture, then y1 has 2 different roles. Do you see the difference in terms of the picture? What makes these 2 pictures different? We'll play Where's Waldo. Yeah, red to blue. So I'm using blue for variance-related terms, and I'm using red for fixed effects, predictor things. So in the first model, y1 and y2 are just related. In the second model, y2 is an outcome of y1. So y1 is a predictor and an outcome at the same time in this analysis. y1 would still be considered endogenous, though, because it is being predicted. So if I wanted to fit this model in M+, I would replace the with in the second phrase here with the on. That creates a directed relationship instead. So that seems straightforward, right? Predictors are exogenous and outcomes are endogenous? No, story doesn't end there.
So in that case, the y1 is the mediator then?
Y1 is the M, that's correct. Yep, so X causes Y, which causes Y2. And in terms of empirical criteria, there is no difference between this top model and this bottom one. They fit the same. They would generate the same predicted correlation or covariance matrix. The difference is entirely in interpretation. So that's something important to keep in mind, is that the way you set up these arrows is entirely up to you. But as long as you have every possible pair of combinations connected in some way, different models with different directions of connections like that will fit the same. They will generate the same predictions. They will be indistinguishable. So this is a semantic distinction, really, more than like a mathematical one. So what parameters get estimated depends on your software and what it's doing with respect to missing data. So if you have an outcome, then each variable that's an outcome will get an estimated intercept, a residual variance if you're in normal land, and any potential residual covariances of it with other stuff. In M+ and R-Lavon, you cannot have missing data on predictors that are truly exogenous. This is exactly the same as what we've seen throughout the semester in any regression model. If you try to fit a regression model of any kind, general, generalized, what have you, cases that have missing predictors are gone. They will get dropped. That is why in most of my examples, I have code at the beginning that says, make sure that all the cases in my data set have all the information that's eventually going to make it into my model, so that the cases, the samples stay consistent across rounds of modeling. So this is bad news. This is not good news. If you have people who are missing predictors, they are gone from your path model. Truly exogenous predictors are not part of the likelihood function, meaning their descriptive statistics are not things that have to get found. What we care about is Y after conditioning on X. But the good news is that predictors don't have assumptions then. So when we talked about conditional distribution fit throughout the semester, and when you talked about assumptions of regression back in intermediate or other linear models classes, we talked about assumptions for Y, right? The Y residuals should look like this. They should fit this distribution. They should be independent and so forth. At no point did we say anything about X. And that's a good thing, because you can have any kind of predictor you want. It can be categorical, continuous, piecewise, whatever you need to have. And this is the point where we're like, what? But I thought if I had full information, maximum likelihood, I could have missing data. No, not unless you do one more thing. You trick it. You trick it into thinking that your predictors that have missing data are outcomes. You can bring your predictor into the likelihood, and Vladimir, this is what you would have to do for your giant generalized multi-level model, and it'll take even longer, but you could fit it in M+ if you wanted to, is to bring it into the likelihood by essentially fitting an empty model for it. Then you can have missing data, because the model thinks it's an outcome from the perspective of estimation. So I will show you how to do this trick. The downside is that you would then have distributional assumptions about your predictor as if it's an outcome, because that's what it is being treated as. So then from the software estimation perspective, it's endogenous, even if it's not really an outcome. If you bring a predictor into the likelihood by saying, hey, estimate its mean and variance, it's an outcome, even if it's not an outcome in the model. That's where this exogenous versus endogenous gets very tricky. By software package, here are your options. So SAS and Stata's original SEM both do full information maximum likelihood. SAS does not have the robust version that allows missing data. Stata has something called MLMV, which is full information and adds robust to it. This forces all predictors into the likelihood whether you like it or not. So if you invoke these estimation options, you are saying every variable in your analysis needs to be multivariate normal, period. Either the residuals of the ones that are predicted or the original marginal distributions of the ones that are not. And this is where older books, you will find statements in older books about path models that say, path models assume multivariate normality. No, that's what the software requires of you if you use these older methods of estimation. That's an important distinction. So here's where I'm going to try to simplify this. Question that you have to answer, is your variable part of the likelihood? It is if it's an outcome. It is if you bring it into the likelihood as a predictor to accommodate missing data, then I'm just going to call it an outcome. If it's not in the likelihood because you don't have missing data on it, it's just a regular predictor like we have in regression, then I'm going to use the word predictor instead. So I'm staying away from this exogenous, endogenous distinction because I think it gets too blurry. We're going to stick with predictor and outcome. You cannot have missing data on predictors the same as usual. You can if you turn your predictor into an outcome. It's a trick. And I will show you the trick because it's very helpful. All right, how are we doing? Question from the back.
Yes, Lisa, and this is about missing data. So before we saw different assumptions about missing data, but in all of those cases we were talking about the outcomes, not the predictors, right?
Yes.
However, here we can extend this idea to talk about the predictors too, because they would be included as part of the likelihood function.
Yes, if we bring the predictors into the likelihood, they are outcomes from the perspective of the estimation, which means you can have incomplete data.
Great.
Under an assumption of missing at random, though. Yes, which means conditionally random, random after you factor in the rest of the information you have. Anytime that you do listwise deletion to remove cases that have missing data, then you are assuming the missingness is completely at random, which is much more strict and unlikely to hold in practice. Unless it's a planned missingness design or something else where you have it under your control. So this is another benefit of fitting path models as opposed to straight regression models, is that you have this option to trick your predictors into becoming outcomes so that they can have missing data. The other option that you have is multiple imputation, which honestly I have never once done in my life because I always go with this trick instead because it's way easier. So I don't want to, is the answer. All right. So vocabulary, we also now have to start thinking and talking about something called model fit. This is an ambiguous term because it can mean a lot of different things. We talked about distribution fit. Some people say fit when they mean effect size in terms of quality of prediction. In this context, though, it has to do with how well your path model represents the means, variances, and covariances of the variables in your analysis. We have never had to worry about this as of yet, because when you only have one outcome, it fits by definition. That one outcome gets its own intercept or its own threshold. It gets a residual variance or a stretchy factor or whatever it has, and that means it's going to perfectly reproduce what you need. When you start having these kinds of path models where, let me go back to a picture, Like if you leave out one of these arrows, then you have the potential to be wrong. You are saying that that relationship is not there anymore. And so fit refers to the extent to which the reproduced relationships among your variables created by your covariances and your slopes adequately describe the original data covariance matrix. That's what model fit means in this context. So this is a new idea that we have not had to worry about just yet. So degrees of freedom is a new concept, has nothing to do with people in path models. Degrees of freedom has to do with the number of variables. It constrains the number of possible parameters that you can estimate at the same time. And to be honest, this is much more of a big deal in structural equation modeling once you have latent variables to the story. In path analysis, you generally don't need to worry about this as much because path models are usually just identified or very close to it. But the number of total possible parameters that you can have is given by this formula here, where V is the number of variables in your model. Variables times variables plus 1 over 2 plus the number of variables is the means. So this total gives you the number of means, variances, and covariances of your variables. So if I had 4, then total degrees of freedom would be this quantity here, 4 times, hang on, I think I did the math wrong here. What's wrong with this? 4 plus 1. I tried to do it twice, so please fix that to 4 plus 1 instead of 5, divided by 2. So then I have 14. That means if I have 4 variables in my analysis, then I can spend 14 parameters to describe them. So I would have to count number of intercepts, number of residual variances, number of slopes, number of covariances against that total. So degrees of freedom in practice is the number of things you left out. Left over is what degrees of freedom means. And in order for your model to work, that number needs to be 0 or positive. It can't be negative. So number possible minus number estimated equals leftover. So if we go back to one of these pictures here, for instance, here's 4 variables. How many different means do my 4 variables have? Softball time. If I have 4 variables, how many means might I be concerned with? Don't think too hard. How many means does each variable need? Sergio, I'm calling on you.
We're not worried about interaction effects in each variable, we just need 1 mean.
Yep. So x1 is a predictor. It would be exogenous, so x1 could get a mean, x2 could get a mean. We brought them into the likelihood then. Now y1 doesn't get a mean, it gets an intercept, but it does the same thing. So if I have 2 means, 2 intercepts, then I have 4 means, 4 parameters, that's even. Should work out just fine. Likewise, variances. Each of these variables comes with a variance. Well, if x1 and x2 are not being predicted, I could just estimate their variance as what it is. Okay, those are good. y1 and y2 are being predicted, so instead of estimating its variance, I estimate its residual, leftover variance. Again, 4 to 4, perfect match. How many covariances are there among 4 variables? I'll let you count on your fingers, but there's a formula for it. How many possible pairwise covariances among 4 variables?
6.
6. How many of those do I have in my model? As shown. Yeah, I got 1, 2, 3, 4, 5. What am I missing? Yeah, this model says that x1 and x2 are unrelated. That could potentially be a problem if these variables are part of the likelihood, because this missing relationship would count against us. If they're not in the likelihood, it's not a problem. But assuming they are in the likelihood, then I have 1 degree of freedom left over for the one thing I left out. That makes my model fit testable, because whether or not I need something else here is a testable question, empirical question. A lot of the time, though, in path models, you would put in all possible relationships and have it be just identified, meaning you spent everything and you can't be wrong. Not so much in SEM, but that's definitely the case in path models. So to be more specific, in terms of information that is going into the analysis and parameters that are coming back out, every variable has a mean that goes in. What comes back out is either an intercept or a mean. Every variable has a variance that goes in. What comes back out is its leftover variance after being predicted, or just the variance if it's not being predicted by anything. And that distinction of being predicted or not results in different labels within M+, for instance, and other software packages too. So if you have a variable that is not being predicted, you get a mean and a variance. If you have a variable that is being predicted, you get an intercept and a residual variance. Same concept though. So for this, most of the time, we would have a one-to-one correspondence and no degrees of freedom left over, which means we don't have room to be wrong. Every pair of variables has a potential covariance, and we can reproduce that either by putting in slopes in which one predicts the other, or residual covariances between outcomes. Either way, we would accurately predict the covariance between the two. Likewise, if we have a predictor and an outcome, we can have paths or covariances there. The latter would bring that into the likelihood. So if any direct sources of covariance are omitted, if there's missing pathways between any two boxes, that's where your degrees of freedom come in. You have room to be wrong, and that constraint is testable. How many missing paths you have and whether or not you got it right. So in terms of vocabulary, is the model estimable? Is your first concern. Did you do anything that would result in a model not being able to work? That just means no redundancy. I have a picture of that, don't I? Yes, next slide. Let me skip to that head. The very bottom of this slide shows an example of something that won't work. If I have y1 predicting y2 and y2 predicting y1 at the same time, you can't do that. There's only one possible covariance between the two, and there is no way given just these two boxes to say how much of it goes one way versus the other. That's not going to work. Don't do that. Is the model testable? Means, do we have degrees of freedom left over? Did we leave out something so that we have the chance to be wrong? So under-identified means broken, means we're trying to do more than we can. Negative degrees of freedom. Just identified means we've spent all our degrees of freedom. We can't be wrong, but we can't test it. And over-identified means we left some stuff out. I had a student develop a mnemonic several years ago. They called this overlooked. So if you overlook certain combinations, it's over-identified. Means you left something out, means you can be wrong by leaving it out. So here are examples of the other two then. So each of these pictures, starting with x1 to y2, is an example of an over-identified model. What it says is that x1 is related to y1, y1 is related to y2. x1 does not have a direct arrow connecting it to y2 though. So this model does predict a relationship from x1 to y2, but only through y1. This is an example of a mediation type of problem. So you have the chance to be wrong to the extent that the true relationship between the first variable and the third variable is not recreated by the middle ones. And you would literally multiply these together to get to be what it would be. Likewise, in the second picture, the arrows go the other way, but it's still over-identified because there's nothing directly connecting x1 and y2. And guess what? These two sets of models have the same fit. They will generate the same predictions. They will generate the same level of misfit in terms of the missing connection between the first and third being gone, but they make very, very different statements. So theoretically, the first model says, no, x1 came first and it predicted y1, which then predicts y2. And then reviewer 3 is like, nuh-uh, y2 came first, which predicts y1, which predicts x1. And you know what? They're both right. There's no way to tell. There was only one instance that I had in my life where I knew the arrows went the right way in a path model. And I got to fight with reviewer 2 about it, in fact. Do you know how I knew which way the arrows should go? Time. In my path model, y2 was collected 5 years later. I win. There is no way that I can cause the past. So I felt good with the arrows going from the past to the future. Anything else would be a much harder sell. But mathematically, these are the same. So you will sometimes hear structural equation modeling and path modeling described as causal modeling. No. Nope. This is a partitioning of a correlation matrix into parameters. It's not causal. Cause comes from design. This picture on the right here is not equivalent, but it is still over-identified. The two-headed arrows do not predict a relationship between x1 and y2 in this case. This is just saying x1 is related to y1, y1 is related to y2, but there is nothing that directly connects x1 and y2 in this. So this is a non-equivalent model that would make different predictions. It would still have 1 degree of freedom though. Just identified is when you've got all the possibilities. So whether you're thinking of these relationships as directional, which is the directed arrows on the left in either configuration, or non-directional, which is the two-headed arrows, these will fit the same. This is just identified. You have not overlooked any pairwise relationships. You cannot be wrong. And then don't do that one. Okay. How the relationships get reproduced is complicated. But there are rules that were invented in, I want to say the 1930s is where this came from. It's very, very old. Yeah. We did not have software to do it, but you can do it via matrices if you had to. I'm not going to make you do that, though. Here is an example that I stole from someone else. Thank you, Jason Newsom. I didn't want to have to redo the picture, so here is his class lecture that I stole this from. Truth in Advertising. So this picture... Yeah, well, yeah, no, that I stole this long enough ago that it would not have had anything to do with ChatGPT, but I have, so in this picture, there's a lot going on, but I've got A, B, C, D, E, and F as my variables here. So let's just look at this here. Is this over-identified or just identified? Over. How do you know that?
Because the F is not directly related to other.
Yeah, E predicts F only. So F is missing a whole bunch of pairwise stuff. A is missing pairwise stuff with E, and not with C, but there's a bunch of stuff missing, point being. So this is over-identified. So then the question is, does this set of relations adequately reproduce the correlations among these variables? That's the question. Because we can't interpret any of the results unless we know that the relationships among the variables are being faithfully recreated. Otherwise, the results are all going to be some shade of wrong. So there are rules about how you can figure out how your model predicts each combination, each variable in pairs of their relationships. So the rules are this: no loops, you can't go through the same variable twice, no going forward then backward, and you can only go across one covariance at a time. So as an example here, if I want to get from variable B to variable D, there are two ways to do that. The most obvious is this path B, which is the slope of B predicting D, right? There's a direct relationship there. But that's not the only way that the model is going to fill in the relationship between B and D. It's also going to happen by going, hey, B is related to A, and A is related to D. So the full relationship would be the B path plus the FA combination. So F is the covariance here, the lowercase, and then the A is the label of the path right here. Now, if you think about that, that is exactly what happens in regression. What you get out of a regression model are these A and B slopes for the unique effect of each variable, taking into account their relationship. So B by itself is incomplete because the rest of the relationship is coming through A instead. So I can go from B to D, and I can go from B over to A, and then down to D, and that would be my full relationship. What I can't do, for instance, if I wanted to go from A to B, I can't go, well, let's go to F, and then B, and then back to A. Like, you can't make a triangle where you go backwards. That one would not work. If I want to go from C to D, there's nothing directly there, right? The model says C and D are unrelated if I just look at this picture, but no, they are related in terms of what's being predicted under the hood. So to get to D, I can go along the two-headed arrow, this covariance that's labeled G, to get to B, and then B picks up. Or I can go all the way from C over to A through the toe-headed arrow that's labeled H, and then down to D from there. So the model is predicting that C and D are related. They're just related in this roundabout sort of way. Like literally roundabout, right? Curved arrows are roundabouts. And I don't know how to draw curved arrows for shit in PowerPoint. Mine are terrible. So I also give him props for making this diagram not look bad. There's lots and lots of graphing packages, though, that can do a better job. That much I know. How about A to E? Are A and E directly connected? Nope, but they're indirectly connected. If I go A to D, D to E, that's one way. I can also go from A over to B, and then B to D and D to E. And I can go from A over to C, and then C to E, C to E. So all three of those pieces then make up the predicted relationship between A and E. And if I want to go A to F, then it's even uglier. So the model is predicting relationships, but as long as you've left out direct relationships between two things, you have the chance to be wrong, and you would want to make sure that it fits adequately, that anything you left out is truly close enough to zero before you would interpret any of the slopes. Yeah. How's that? Complicated. And you're probably thinking to yourself, oh my God, is she going to make us compute this stuff? No, I'm not that mean. I will show you in the output where the section is that says, what does the model predict my relationships to be? You will get a matrix that has it. And then you have another one that shows up, what is it for real? And then literally, what was it for real? What did it say it was? What's the difference? The difference is your misfit. So as part of your output, you will see what it should be, what your model thinks it is, and how far off you are. And that will help you figure out what all needs to be added back in order to make it fit. If you are using unstandardized results, then all of what I said needs the variances of the predictor variables to be attached to it as well. So then these formulas get even more complex, which is why I didn't do it that way. So here's a short example to demonstrate these ideas. Let's say that I have x1 and x2 as my predictors, but I brought them into the likelihood, so the model thinks they're outcomes. I think they're just correlated, so I put a covariance between the two of those. I think each of these predicts y1, and because they predict y1, y1 predicts y2, and that way x1's relationship to y2 and x2's relationship to y2 are supposed to happen through these middle paths right here. Okay, in terms of how each box is being predicted, x1 and x2 aren't being predicted, right? They look like predictors. So all they have is an empty model. They will get a mean, and they will get some kind of variance. y1 and y2 are outcomes, so they get intercepts, they get slopes of all of the variables that are predicting them directly, and then they get residuals, residual variances separately for each one. So in terms of what's going to be right and what's going to be wrong, 4 of the 6 covariances are going to be right because they are the ones that have direct relationships between the two that would fill in any gaps relative to what they're supposed to be. So x1 and x2 covariance is going to be right because I put it in there directly. That one's nailed down. Likewise, x1 and y1 is going to be right because of this direct path as well as the covariance between that to get over from x2 to x1. So the predicted covariance between the two is a function of those two things. The variance of x times the slope plus the covariance times the slope of the other variable. x2 and y1 perfectly recreated for the same reason. y1 and y2 perfectly recreated because of this path right here. So the ones that have the potential to be wrong are x1 to y2 and x2 to y2 because we don't have anything directly connecting those. The model implied variances are going to be right so long as you let each variable have a different variance as part of the analysis. So the variance of y1 is a function of how much of it comes from x1, how much of it comes from x2, the covariance between the two times 2, since covariance matrices are symmetric, plus leftover. Same, y2 is even uglier because of all the extra paths, but they can't be wrong. The ones that have the potential to be wrong are the ones that are missing a direct relationship. And so here's what the model would say that they should be. And our question is, did we screw up by not having something directly between x1 and y2 or between x2 and y2? That's what we need to know. All right. 307, how we doing? So here's a whole bunch of crap that's next about fit. There's a lot of letters and acronyms involved in this. Am I right? Got laughter in the back. Yeah, I keep it real, folks. It's a whole bunch of crap about fit. Here's the thing. If you keep your path model just identified, you don't need to worry about it. It fits. Fit just means that you have adequately recreated all of the relationships in your data. It doesn't say what they are or whether they're any good. It just means they're adequately recreated. So let me answer a question and then let you go that I get at least once a semester from somebody, either in class or on the internet. This is slide 30 that I'm skipping ahead to. Let's say that I have a path model that looks like this, and it fits very well by all of the letters that I'm about to introduce next week. But none of the relationships are significant. How can that be true? Fit means that I have adequately recreated the relationships in my data. It does not mean that I have relationships worth recreating. So if I have non-significant paths connecting all of my variables, that's just reflecting the lack of correlation that I have. My model has adequately captured the lack of relationship between these variables, and that lack of relationship is given by the strength of these coefficients. So fit and effect size are still two different things. Fit means have you adequately captured the relationships? Effect size is what are those relationships? So now you know. You can have a good fitting model that's useless. Not better. All right. Questions? Go back to the slide here. Algebra. Yay. I don't need you to memorize this. Here's what I need you to take with you, okay? You leave something out, you could be wrong. So you got to make sure you're not wrong before you look at your results. Okay? That's it. Hang on to that much. And I will show you several examples, most of them just identified because I don't like the chance of being wrong in path models. All right, 309, shall we call it a week? Why not, right? Take 5 whole extra minutes of freedom on me. Go enjoy a tornado-free afternoon. I know, right? It's not over yet, but let me know if you need anything. Otherwise, I hope to see you all next week. Have good weekends. Thanks for being here.